Hello, everyone. In this example, we're going to talk about yield strength, and we are going to determine the minimum factor of safety based on yielding according to the maximum shear stress theory and minimum factor of safety based on yielding according to distortion energy theorem. A round shaft supports a transverse load of F equals 15,000 pound force and carries a torque of T equals 7 kips inch as shown in the figure. The shaft does not rotate. The shaft is machined from AISI 4140 steel, quenched and tempered at 400 degrees Fahrenheit. Document the location of the critical stress element and how you determined it to be critical. Do not assume transverse stress is shear stress is negligible without proving it. Then determine the minimum factor of safety based on yielding according to the maximum shear stress theory, and determine the minimum factor of safety based on yielding according to the distortion energy theory. So first thing is to draw a free body diagram. We see that this is comprised of three sections. So we can translate it to the 2D plane by drawing this free body diagram. So we have our first section here, second section here, and third section here. So we will call this first section A, the second section B, and this third section C, as shown in the diagram. So at A, there is a reaction force pointing upwards. We can call it RA. And at um oh yes, and then sorry, this end is called D. So at D we have a reaction force pointing upwards too, which is RD. So first things first is to determine the reaction force. And since this whole structure is in mechanical equilibrium and the end A is free, we get a zero net moment at A because A is not fixed. If A were a fixed end, there would be a moment at the wall too. But over here it's free, so there is no moment. So we can do a sum of moments around point A or point. Um, yes, we can do a sum of moment around A. So sum of moment around A will be equal to 0. Um, so we have that the sum of moments around A is equal to 0, and it is equal to, oh, and we have a force pointing down here. So F. It's equals to negative 2F because this distance is 2 inches. And it's negative because F rotates this clockwise. So we have negative 2 inches times F plus 3 inch RD because RD is located at 3 inches from A. So it will be 3 inch times RD, and RD rotates the structure clockwise. So solving for RD, we have that RD is equal to 2 over 3 F. And plugging in our F value at uh 15,000 pound force, we have that F is equals to so RD is equals to um 2/3 15,000 pound force. which is equals to 10,000 uh pound force. And we can convert this to kips. One kip is equals to 1,000 pound force, so 10,000 pound force will be equal to 10 kips. So now we can solve for the reaction force at A by using force equilibrium because we know that the sum of moments of an object in equilibrium must be equal 0 because the object is not turning or anything. And also the sum of the forces. So the sum of the forces in the y direction must be equal to 0 since the object is not moving in the vertical direction. So it'll be equal to the sum of all these vertical forces, which is RA plus RD. And here we're taking the vertical direction upwards to be positive. And then minus F is equal to 0. So then we have that RA minus 10 kips um minus F, so F is 15 kips. Wait, sorry, this is plus FD, so plus RD, sorry. And then minus 15 kips. And this gives us that RA is equal to 5 kips. Um, since all this is equal to 0. Sorry, I should probably write that equals 0. And then RA is equals to 5 kips. So using these reaction forces RA and RD, we can now draw our shear stress and bending moment diagrams as we will do in the next section. Note that the section of interest are all the sections we have any kind of discontinuity, um, such as an external load if in the form of force, moment, or torque, or any sudden changes in geometry such as at section B and C, where one shaft is joined to the other one. Um, the critical locations will be at the points B and C, where we will have maximum transverse shear or bending stress, because both locations will also have torsional shear stress. Also note that since there is a discontinuity or a change in the shaft diameter at the point B, we will choose the small diameter, which is this diameter over here, approaching the point B from left. And this is because a smaller diameter will be more conservative because it will give a higher stresses. And we want to be conservative with our calculations. So let's now draw our shear diagrams and bending moment diagrams. So now we will draw the shear moment diagram and bending moment diagrams. So shear moment diagram is Vx over Vx against the position. So we will have to graph our position of the shaft on this diagram over here. We start at A, then we move to B, then we move to C, then move to D. So as we see over here, the reaction force at A, which we begin, is 5 kips. So it will be positive 5 kips. 5. And this is in kips. And this is position, X. Let's call it X. So the 5 kips will deal from A to B because, or rather A to C, sorry. Because the reaction force is only at here, and then we don't have another force until point C. So it will go all the way to C. And then at C, we have a sudden drop because of this force over here. which is 15 kips, negative 15 kips. So the force will drop down 15 kips. So down 5 kips and then down another 10 kips. And it will end up at negative 10, which is over here. And this 10 kips will remain until we get to point D. And then at point D, we have another jump, RD equals 2/3 F, which is we found to be 10 kips. So this 10 kips will be uh, plus, because it's pointing upwards, so plus 10 kips and back to 0, which makes sense because um, our beam is in static equilibrium. Now we will draw the bending moment diagram, and don't forget to label your diagram Vx. Um, so our bending moment diagram will be continued here, and often it is helpful to draw these lines downwards. So mx So as we noted earlier, there's no existing moment at point A or point D because both ends are free. They are not fixed to a wall, so the wall does not exert a moment on the beam. So we will start at 0. And as we see, the area under the graph of the shear stress diagram will give us a certain value on the moment diagram. We see that we have positive areas, so this will translate to a positive slope on our bending moment diagram. And we can calculate the bending moment at each of these critical points. And these points are critical because, as we said earlier, there are points at which there is a discontinuity, such as at B and C, but not really at D. But B and C are the critical points we have to calculate the bending moment for. So first we can just draw a general slope since we know that it will be sloping up until C because all this whole area is positive and increasing linearly. So we have a linear slope. And at point B, we can calculate the bending moment as this area under the curve over here, which is equal to 5 kips times the distance from A to B, uh, which is 1 inches. So 5 times 1. So this one will be 5 kip inch. And at C, we will take this larger area under the curve, this whole area under the curve, and it will give us 5 times 2 inches because the distance from A to C is 2 inches, as we see on this diagram over here. So it will be 5 times 2, which is 10 kip inch. Um, Yes, so then the moment will return back to 0, and this time the slope will be negative x as indicated on the shear stress diagram because the area under the curve is negative and it will return to 0, which expected because the moment at D is 0. And how we can understand this is that CD is negative 10 times 1, which is negative 10 kips. So negative 10 kip inches. Um, so we go from 10 kip inch and we subtract, we add negative 10 kip inch. So it will return us back to 0 as we expected. That's how you know that the bending moment diagram is drawn correctly. So basically we have 2 points, critical points we want to evaluate, B and C. We will start with point B. So point B. And we will use the smaller diameter, which is 1.1 inch diameter for point B, because the smaller diameter will be more critical. So Um, we first have to find there is a shear stress due to torsion because as you twist this shaft over here, it'll create a shearing stress on the face of B that goes like this and decreases as you go towards the center. And the maximum shear stress for torsion is given at the outer radius, which is this portion over here. And we can find that equation from an equation sheet as being for torsion, as we see, tau max is equals to tau times r over j, or tau in general is just equals to mm, tau times rho over j, where rho is the distance from the center. But here we are interested in the outermost location, which is tau max. And J is the polar moment of inertia. And for a circular cross-section, it's going to be pi times d4 over 32. So we will use J along with our equation for tau in order to solve the problem. So now using what we know, we have that tau torsion is equals to the torque times rho, the radial distance, over the polar moment of inertia, which is thus equals to T times the diameter over 2 over pi times the diameter to the power of 4 over 32. And over here, the diameter that we were concerned with is the 1.1 inch diameter because this is the critical location because it's a smaller diameter for part B. When we could have picked the 1.5 inch diameter also because that's also for part B, but we picked the 1.1 inch diameter because that is more critical since it is a smaller diameter. And this simplifies to 16 times the torque over pi d cubed. Um, and this gives us, if we plug in 1.1 inch for D, we will get 16 times 7 kip per times inch over pi times 1.1 inch cubed. So this will give us 16 times 7 divided by pi divided by 1.1 cubed, which is equal to 26.78. 26.78 kips per square inch, KSI. Now, at location B, there is also a bending stress. There is an axial stress due to bending as well. Mm, As we see over here, our normal stress for a beam and bending is given by sigma equals the moment times c over I, where I is the moment of inertia, and is pi over 64 times d to the power of 4 for a circular cross-section. So back to our problem over here, we thus have that sigma bending maximum is given by the moment at B, which is 5 kip per inch. But we'll first write the general form, which is MC over I. So this is equals to M, and C is uh going to be where the maximum bending stress occurs, which for a beam, if you remember from mechanics of materials, is going to be at the very top. Because at the neutral axis, for instance, it lies along the neutral axis. So when you bend the beam upwards like this, um, a stress element located at the neutral axis doesn't experience a normal stress, but one at the top will experience a normal stress. And stress element here will be, for instance, in tension, while the ones over here will be compressed because you're bending it inwards, and over here it's flayed outwards. But the ones at the top will experience the most significant stress because it lies furthest from the neutral axis. Um, yeah. So with that in mind, our C will be simply the radius, which is d over 2. And then I is the polar moment of inertia, which is going to be pi times d to the power of 4 over 64. Simplifying this, we have 32 times the moment over pi times the diameter cubed. And the moment, again, we use 5 kips inch. So 5 kip inch. And for the diameter, again, we use 1.1 inch. Since again, that is the critical smaller diameter um for location B. 32 times 5 over pi over 1.1 cubed is equal to 38.26 KSI. So don't forget that for part A, we're concerned with the minimum factor of safety based on yielding according to the maximum shear stress theory. So for maximum shear stress theory, we first have to find the maximum shear stress. As we see on our equation sheet, the maximum shear stress MSS theory for the materials is N equals to the yielding strength over 2 times tau max, which is the shear stress, which is SY over principal stress 1 minus principal stress 3. So I think we forgot to define the coordinate axes. So this is Y, this is X, and this is Z. So X, Y, Z. And basically, for this portion, we have so far been only considering for the plus Y and negative Y B faces. And these are all the stresses acting on those faces that we were talking about so far. Um, so basically the tau max for the plus Y and negative Y B faces is going to be equal to the square root of sigma x plus sigma y divided by 2 squared plus tau squared as a general form. And we get this from our equation sheet. Or I guess not, but this is from the Moore circle chapter. Mm, and this is equal to, since on the plus y and negative y b faces, we only have really, mm, I think it is sigma x. Yes, I think sigma x is going to be our maximum bending stress. So we only have square root of um sigma x over 2 squared plus tau squared. And the tau comes from the tau torsion because that is the only tau in this case, squared. And the sigma x is going to be equal to the sigma bending maximum, which is 38.26 KSI. And as a result, we'll get that the tau max is equal to, and the T torsion is 26.78 KSI. So we have 38.26 divided by 2 squared plus 26.78 squared. And we take the square root of that. And we get that it is equal to 32.9 KSI. Now, we can apply our factor of safety for yielding strength at for the maximum shear stress theory as this equation from our equation book. So N is equal to SY, the yielding strength, over 2 times tau max, which is equal to that. So factor of safety for yielding at MSS is thus equal to the yielding strength over 2 tau max. And we have to find the SY value for our steel, which is AISI 4140 steel. And we find that from our diagram. This is the diagram we use, which is AISI diagram. And we find that the yield strength is going to be for AISI 4140 is quenched and tempered at 400 degrees 400 degrees Fahrenheit. So we will get a yielding strength of 238 kpsi, I believe. So 238 kpsi, and then we have that factor of safety at yielding for MSS is equal to 238 over 2 times 32.9, which is equal to 238 divided by 2 divided by 32.9, 3.62 kpsi. Oh wait, no, sorry, not kpsi. This is the factor of safety. So this is one of our factor of safeties. Um, Now while we're here, we can actually solve for part B, of for phase B. Um, the factor of safety based on the based on the distortion energy theory, and we use this equation over here. So we can use not the principal stress form, but the second one down here, because we are concerned with sigma x and sigma y here, we didn't really solve for the principal stresses. So we can use that form and then calculate the factor of safety as n equals the yielding strength over sigma prime. So I've copy and pasted the equations here. And so let's calculate sigma prime first. Sigma prime will be equal to 1 over root 2 square root square root of sigma x is going to be sigma bending maximum, which is 38.26. And then there's no sigma y, so minus 0. So it's just 38.26 for the first term here. For the second term, we have no sigma y. So we have, and no sigma z, so it is plus 0 squared. For the third term, we have only sigma x, so sigma x was just 38.26 squared. And then plus 6 times all these shear stress terms. Well, our torsion term over here is our only shear stress term. And which face is it acting on? Well, we can draw a little diagram. So we are concerned with this part where the diameter is 1.1 inch. And the torsion stress, because we are twisting it this way, so at this location, the vector will point this way and the vector of shear stress will point this way on the bottom direction. So it's basically acting on the x face in the z direction. So tau xz will be our tau here. But it doesn't really matter because we just know we have one tau term. So torsion, we will use the one for torsion that we found, which is 26.78. 26.78 squared. And then we calculate this to be 60.13 KSI. And then now we can calculate the factor of safety for yielding, Ny, for distortion energy theorem, Ny comma MDE. And that is equal to the yielding strength, which we found to be 238 kpsi. 238 kpsi over 60.13. And that is calculated to be equal to 3.96. We have now calculated the factors of safety for the plus y and negative yb faces. And these are the faces located here. Plus y and negative y face. However, we now have to consider for part B the negative z face, which is from this direction, which is this right face over here. There is no normal force due to bending moment on this face since this face is located at the neutral axis. So as the beam bends, the stress element over here will not be in tension or compression because it's located at the neutral axis. However, there is still going to be shear stress from torsion at this negative z location because as we twist the shaft, we have vectors, shear stress vectors going this way. And at this location, there is an associated shear stress vector as well. There's also going to be transverse shear stress. Now, what is transverse shear stress? Transverse shear stress is also a result of bending moments, but it's the result of the stress acting on the cross-section of a beam or similar structural element due to a load that tends to cause the element to bend. As we try to bend this element, for instance, um, there's going to be, because of these two forces, these layers in the beam are going to slide past each other. So that results in our transverse shear stress. And the maximum transverse shear stress typically occurs at the neutral axis of the beam, which is why we have to consider our Z minus face over here, the right face, because it's at the neutral axis. And transverse shear stress is located at the neutral axis. Transverse shear stress looks something like this. Is drawn as such, so smaller arrows from the top, and it has a parabolic distribution, and the arrows increase, and when it reaches the center, the transverse shear stress is the largest. In general form, transverse shear stress is given by um, a A star, Y bar star. Let me remind myself of the formula. Times V over IT. However, for these type of problems, we only have to be concerned with the maximum transverse shear stress since we are concerned with the limit conditions, the maximum stress that is going to have to sustain. So we know that our maximum transverse shear stress for a circular cross-section is equal to, from our equation diagram, 4V over 3A. And again, I think this formula is not on the equation sheet, so you have to memorize it yourself. Okay, so for the I'm gonna write it more cleanly now. This is the Z minus phase that we're concerned with. And at that phase, as we mentioned earlier, there is also torsion, shear due to torsion. And this is actually the same as we found earlier, since torsion is only a function of the radius over the oh wait, sorry, over the polar moment of inertia. And the polar moment of inertia doesn't change, and the radius is also the same. So we find that it's equal also to 26.78 kilopascal, 78, oh sorry, 26.78 kips per square inch. And we now have the transverse maximum shear stress for a circular cross section. The maximum shear stress is given by 3V, oh sorry, 4V over 3A, where A is a circular cross section at point B using the smaller diameter because the smaller diameter is more critical. It's going to be 4 times the shear stress at B, which we found to be 5 kips. Um, over 3 times the area at B, which is pi times the diameter of B, so 1.1 divided by 2 to get the radius and the radius squared. And if we calculate this, we get that the maximum transverse shear stress is 7.01 kips per square inch. Um, so as we mentioned earlier, the normal stress due to bending is at this face is 0 since this face lies on the neutral axis of the shaft. So we now have two shear stress components, so we have to figure out a way to add those up. Let's first figure out whether they point in the same direction. So, yes, okay, we already have the diagram over here, so I'll use this. So the torsion is going this way. So as we mentioned, the torsion vectors are going like this. So the shear stress due to torsion is pointing up. And also, we have transverse shear stress due to the forces that are trying to bend this whole structure. And the transverse shear stress, we don't know the direction yet, but I'm just going to draw it like this. Is also pointing down, so in the same direction along the y-axis. So we can just add these two components up since they are both pointing in the y direction. So we then have, yes, actually transverse max. Yes, we will have that the total shear stress is equals to the shear stress due to torsion plus the shear stress due to transverse, and it's equal to tau. And now we use that equation from earlier to find the maximum shear stress on this face. So tau max is equal to the square root of sigma x plus sigma y over 2 squared plus tau squared. Sigma x plus sigma y over 2 squared is equal to 0 since there is no bending stress at this negative z face. And then thus we are left with square root of tau squared, which is equal to the square root of tau torsion plus tau transmax, which is equal to simply tau, yes, which is equal to 26.78 plus 7.07 KSI, which is equal to 26.78 plus 33.8. 33.8 KSI. So now that we have our tau max, we can again use our equation for the maximum shear stress theory. So the factor of safety for yielding due to the maximum shear stress theory is going to be equal to SY over 2 times tau max, which is equal to, again, our SY value was 238 kpsi. 238 kpsi over 2 times tau max, which is 33.8 KSI. And do note that KPSI and KSI are actually equal because one kip is equals to 1,000 pound and one KSI is 1,000 pound per square inch. So when you're saying 238 kilopounds per square inch, you're actually saying 238 kips per square inch because one kip is 1,000 pounds. 238 KSI divided by 2 times 33.8 KSI. This is equal to 238 divided by, oop, 238 divided by 33.8, oops, divided by 2. So it's equal to 3.52. Now, while we're at it, we can also calculate um the factor of safety for yielding for the distortion energy theorem, which is going to be equal to the yielding strength over sigma prime. And sigma prime again is given by this equation over here. Yes, so then SY, so NY according to maximum distortion energy is equal to 238 kpsi over, oops, oh wait, sorry, we have to calculate sigma prime first. Sigma prime is equal to 1 over root 2 square root of, over here, sigma x and sigma y and sigma z are all 0 since there is no normal stress due to bending. So we can get rid of all these three terms and we are left with only the shear stress terms. And our shear stress terms are going to be the tau xz because it's acting on the x face. Wait, no, actually it's going to be, yeah, it's acting on the x face in the y direction. So it's going to be tau xy. But it doesn't really matter. We just know that we have only one shear stress term. So it's going to be square root of 6 times tau xy squared, which is equal to 1 over root 2 times square root of 6 times tau xy square root of 6 times tau xy, which is 1/2, or 1 over root 2 times root 6 times tau max, which was equal to 33.8 KSI. So we get that sigma prime is equal to 58.54 KSI. Now, we want to plug this into our factor of safety equation. 238 KSI over 58.54. And this will give us 4.07 as our factor of safety. We've now calculated all the factor of safeties for our for location B. Now we have to move on to location C. So for the part C, point C, we also have two locations. First, you're going to start with the positive Y and positive and negative Y faces. And again, we are going to use the smaller diameter for point C. So approaching from the right, the smaller diameter will be 1.3-inch diameter. And for the y plus and y negative faces, will be these two locations. Except for point C, which will be these two locations. So for these two locations, we have shear stress due to torsion and a normal stress due to bending, but we don't have transverse shear stress because transverse shear stress, when the element is located at the top, transverse shear stress is 0 because transverse shear stress is of the form V A bars Y bar star over IT. And when the stress element is located at the top, there's no area above that stress element. So that's why transverse shear stress at the top location is 0. So we will focus on the torsion. Shear stress due to torsion at maximum location will be at the radius, but in general form is given by torque times rho over the polar moment of inertia. N is equals to torque times d over 2. This is the general form over pi d to the power of 4 over 32. And this simplifies to 16t over pi times d cubed. And this is equal to 26.78 KSI. As we found, oh wait, sorry. That is for point B. But the general equation remains the same, except we have a different diameter, since the diameter we're using is 1.3-inch diameter. So we have 16, and the torque is going to be the same because of conservation of torque. So torque is still 7 kips inch. So we have 7 kip inch over pi times the diameter, which is 1.3-inch. And this is equal to 16.2 KSI. And now we will calculate the normal stress due to bending. And this will actually be in the x direction. And how do we know that? Because as this beam is bending, whichever way it's bending, the stress element will along here will be in compression, and this is pointing to the x direction. So that's how we know it's located in the x direction. So x direction. And that one is equal to MC over I in general form, as we did earlier for part B. And the moment here is going to be the moment at C. And the moment at C from our bending moment diagram was found to be 10 kip inches. So equal 10 kip inch. And then C is going to be the location of the stress element from the center. So it's going to be the radius, which is again going to be 1.3 divided by 2. And the moment of inertia of a circle is pi times d to the power 4 over 64. Actually, let's write all of this in general form first. It's always a good idea so that we can simplify things before we plug our answers in. And this is equal to 32 times the moment over pi times d cubed. And this is equal to 32 times a 10 kip inch over pi times d, which is 1.3 inch. And if we solve this, it will be equal to 46.36 KSI. So now again, we calculate the tau max for the positive y and negative y phase at point C as being sigma x. And this equation for tau max is found from the Mohr circle. You can use the Mohr circle too, or you can just apply this equation directly. Over 2 squared plus tau squared. So over here, we only have sigma x. So this simplifies to sigma x over 2 squared plus the shear stress from torsion, tau torsion. So then it is equal to the square root of 46.36 over 2 squared plus 16.2, which is equal to this one is supposed to be squared, so it's 28 KSI. Now we use this tau max value to calculate our factor of safety for maximum shear stress theory and maximum distortion energy theory. So again, for maximum shear stress theory, we have that the factor of safety is equal to SY over 2 tau max. Yep. Equal, what is our SY again? 238 2 times 28.28 just equal to 4.21. Now now for our maximum distortion energy theory, remember that we have to calculate sigma prime first, according to this equation. And basically, according to this equation, we get that sigma prime is equals to 1 over root 2 times square root of sigma x is going to be sigma bending maximum, which is 46.36. And here we have no sigma y and sigma z. So it'll be 46.36 plus 46.36 squared plus 6 times and we have to ask ourselves, how is the shear stress acting? The shear stress is acting on the x face in the z direction. So it'll be tau xz, as we also similar to what we did for part B. Tau xz, so tau xz is equal to tau torsion, which is equal to 16.2 ksi squared. So sigma prime is equal to 54.19 KSI. Now our factor of safety for maximum distortion energy is equal to NY MDE equals to SY over sigma prime, which is equal to 238 over 54.19, which is equal to 4.39. Okay. Now let's consider for point C, the right surface of Z negative face. So this is the face that looks like this here. And on this face, there is only gonna be shear stress because it's located on the neutral axis. So there's no normal stress due to bending. So yes, we will have shear stress due to torsion because we have torsion at this location too. The torsion is going this way. So shear stress at that location will be that due to torsion, and at this location will be this due to torsion. And basically tau torsion is equal to the torque at maximum is equal to torque times the radius, but in general form it's T times rho over J, where J is the polar moment of inertia. So we will have torque times Z over 2 over pi d4 over 32, which is equal to 16t over pi d3. We have thus 16 times the value for the torque, which is equal to 7 kips inch. 7 kip inch divided by pi times d to the power of 3. So the diameter is 1.3 inch. So the The shear stress due to torsion is um, equal to the one we calculated earlier, which is 16.2 KSI. Okay. And now we have another transverse shear, though. And it's the maximum transverse shear that we're concerned with for a circular cross-section. And the formula is given by 4V over 3A, where A here is the area of the face of C. And it's equal to 4 times the shear stress at C, which we calculated from the bending moment diagram to be um, negative 10 kips. So 4 times 10 kips over 3 times the area of that face, which is pi, times 1.3 over 2 squared. So this value will be equal to 10.05 KSI. Now, similarly for part B, the torsion shear stress vector and the transverse shear vector point in the same direction. So we'll be adding them up as tau is equal to T torsion plus T trans max. And I think that sign does matter here, but they are pointing in the same direction. Both of them are pointing down, I think. So we can simply add them up. But also later on it's going to be squared in this equation. Tau max is equal to square root of sigma x plus sigma y over 2 squared plus tau squared. Because we don't have any normal stress due to bending, so sigma x and sigma y are both 0. So we're left with equal to tau squared equals tau equals tau torsion, which is 16.22, and tau transmax, which is 10.05. And this gives us that equals 16.22 plus 10.05, which is equal to 26.27 KSI. Now we will use this tau max to calculate again the factor of safety due to the maximum shear stress theory, which is equal to the yield strength over 2 times tau max, which is equal to 238 over 2 times 26.27 KSI, which is equal to 4.52. And now for our factor of safety due to maximum distortion energy theory, again, we have to find sigma prime. So let's do that first, according to this equation. Sigma prime is equal to 1 over root 2 times, but sigma x, sigma y, and sigma z are all 0, so we are left with square root of 6 times, let's see the direction of the shear stress. So it's acting on the x face in the y direction. So tau xy which is going to be uh the tau is going to be the tau max that we found, which is 26.27 KSI squared. And this gives us that sigma prime is equal to 45.50 KSI, and then thus the factor of safety due to the maximum distortion energy theory is SY over over sigma prime, which is 238 over 45.5 equals 238 over 45.5, 5.23. So that is our factor of safety. And let's see which one is the minimum. Let's retrace our steps. So for maximum shear stress theory, we have 4.52, 4.21, and 3.52. Obviously, 3.52 is the smallest one, so we can conclude that the minimum uh, factor of safety according to maximum shear stress is equal to 3.52, which occurs at the section B. On the right side of the shaft. So for B, we have for maximum distortion energy, factors of safety 5.23, 4.39, and 4.07. Obviously, wait, hold on, am I missing something? So it's 5.23, 4.39, 4.07, and 3.96. Yeah, so 3.96 is the smallest one. Min factor of safety according to maximum distortion energy theorem is equal to 3.96. Located on section B on the top and bottom faces. So this concludes this lecture. I hope that it helps you solve this problem and understand more the factors of safety. Here's a quick recap of the problem. So we started with our bending moment diagram. This is the most important part, but before that, we have to find the reaction forces. And we observed different phases. We divided the shafts into three parts to identify the critical locations. The critical locations are areas with highest bending moment and shear stresses, as well as when the shaft is joined to another part. But ultimately, we identified different phases where they are subjected to stress, and we calculated the factor of safety for each phase, for each point, critical points. And after that, we compared all the factors of safety, and we found and we chose the smallest one for each shear for each factor of safety theory. So I'll go over the whole problem one last time, scrolling slowly so that you guys can recap the whole problem. These slides will be posted in the lecture video as well. Thank you for watching.